Today we'll begin our discussion on the theoretical basis or the background theory for mathematically deriving the code specified formulations for design earthquake loads that are prescribed by the latest revision of the Indian Seismic Design Code, that is IS 1893 Part 1, 2016 revision, the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, and then in the subsequent lectures we will continue with the discussion of the background theory or the theoretical basis for mathematically deriving the code specified formulations for the design wind loads that are prescribed by the Indian Standard Code of Design Practice for calculation of wind loads, that is IS 875 Part 3, the 2015 or the latest revision for calculating the wind loads acting on building structures. Now, it is worthwhile to note here that the principles and the fundamentals that form the theoretical basis for the mathematical derivation of the code specified formulations for design earthquake loads as well as design wind loads are common to all building structures regardless of the building material or the primary construction material that is implemented for the construction of the building. In other words, the background theory that underlies the code specified formulations for calculating the design earthquake loads as per IS 1893 Part 1, the 2016 revision, as well as the theoretical basis underlying the code specified formulations for calculating the design wind loads as per IS 875 Part 3, the 2015 or latest revision, are the same for building structures irrespective of the construction material or the building material, regardless of whether the construction material is concrete or steel. However, since our discussion is in the context of the structural design of reinforced concrete frame building structures, the principles and fundamentals will be discussed and illustrated based on examples from examples of reinforced concrete framed buildings. With that background or introduction, we will proceed to our discussion on the theoretical basis for mathematically deriving the code specified formulations for design earthquake load first, and then in the subsequent lectures we will continue the discussion of the theoretical basis of the background theory underlying the code specified formulations for calculation of design wind loads for building structures. Well, before I begin my discussion on the topic for the next few lectures, that is the theoretical basis of the code specified formulations for calculating design earthquake loads and design wind loads, I would like to highlight the objective of the discussion, or the objective of the next few lectures. And in the next few lectures, the objective of the discussion will be to derive the code specified formulations for calculating design wind loads first, and then subsequently design wind loads afterwards, starting from the first principles of mechanics and physics to arrive at the theoretical formulation that forms the basis for the code specified formulations for design earthquake loads or design wind loads as applicable. In other words, we will be starting from the first principles or fundamentals of structural dynamics based on theory of dynamics of structures to derive the code specified design formulations for calculation of earthquake loads in the first few lectures, and then continue similar discussion with the objective of mathematically deriving the code specified formulations for design wind loads, starting from first principles of fluid mechanics and boundary layer flow in case of the wind loading acting on building structures. Well, in order to understand the theoretical basis for mathematically deriving the code specified formulations for calculating the earthquake loads on building structures, it is useful to acquire an insight or an intuitive understanding of the physical response of building structures to earthquake ground motions. That is uh, an intuitive understanding of the mechanics of the structural response of a building structure to an earthquake is necessary for deriving the code specified formulations for calculating the earthquake loads on a building structure from first principles. In simple words, we need to have a physical understanding of the effects of an earthquake ground motion on a building structure. Well, with that objective in mind, we will have a brief review of the structural effect of an earthquake on a building structure in order to physically visualize the structural response of a building structure to an earthquake ground motion. Now, earthquakes cause random motion of the ground in all the three directions, that is, all three dimensions, and the intensity of the earthquake ground motion at any building site at which an earthquake occurs depends on four important factors. One, the magnitude of the earthquake, for example, the intensity of the earthquake measured on the Richter scale or as peak ground acceleration. Two, the depth of the focus, that is, the source of the disturbance that occurs deep inside the Earth's crust, resulting in the seismic waves traveling in all different directions from the source and arriving at the surface of the Earth, including the building site. Three, the distance of the building site from the epicenter, that is, the point on the Earth's surface that is vertically above the focus or the source of the disturbance. Four, the soil strata or the soil medium that is below the foundation of the structure at the location of the site, since the seismic waves are transmitted through the soil medium, and therefore the properties of the soil medium or the soil profile at the location of the building site can alter, that is, amplify or and attenuate the seismic waves. Now, for the purposes of mathematical modeling of an earthquake ground motion, for structural analysis of the building structure under the influence of the earthquake ground motion, an earthquake ground motion can be represented as an acceleration, velocity, or displacement function of time, that is, a time variant function of acceleration, velocity, or displacement termed as an acceleration, velocity, or displacement time history, respectively, in all the three dimensions. The ground accelerations are the easiest to measure, since ground accelerations that are caused by an earthquake ground motion can be measured using accelerometers, that is piezoelectric accelerometers installed at an earthquake site, usually in an observatory near the earthquake site or the building site. And therefore, the mathematical modeling of an earthquake ground motion for the purposes of the dynamic analysis of a building structure to theoretically predict the dynamic response of a building structure to an earthquake ground motion. The exercise termed as seismic analysis of the building structure is most commonly performed by representing the earthquake ground motion as an acceleration time history, that is, time variant function of the acceleration with respect to time. Generally, horizontal and vertical components of ground accelerations are recorded as functions of time, since both the horizontal and vertical components, with the horizontal components being in the two horizontal orthogonal or principal directions x and y, for example, and the vertical component acting in the vertical z direction, for example, are significant or considerable to result or induce earthquake vibrations or vibrations of the structure under the action of the earthquake. Now, just for an idea or a sense of the magnitudes of the ground accelerations that can be induced by an earthquake at a building site, the peak ground acceleration, also commonly abbreviated as PGA, measured during the San Fernando earthquake of 1971 at the Pacoima Dam site, exceeded 1 G, which is quite a significantly large magnitude, that is 9.8 meters per second square. Qualitatively, the effect of the earthquake ground motion or the seismic ground excitation that occurs at the building site on the dynamic response of the building structure to the earthquake depends on three general parameters. One, the material form, size, and type of construction, which determine the dynamic properties or dynamic characteristics of the structure. For example, the stiffness, mass, and the viscous damping or the natural damping of the structure. The nature or the profile of the foundation soil, since the soil medium is underlying the foundation of the structure, and the seismic waves have to travel through the soil medium, and the properties, the dynamic characteristics or the dynamic properties of the soil medium or soil strata underneath the foundation can significantly modify the wave properties or the amplitude and the frequency characteristics of the earthquake or seismic waves. As an example of the significance of soil strata or nature of the soil medium underlying the foundation of the structure in determining or influencing the dynamic response of the building structure to the earthquake. The Mexico City earthquake resulted in extensive and severe damage to the building structures, not because of the intensity of the earthquake, which was a moderate earthquake in terms of the peak ground acceleration, but because of the amplification of the seismic waves or the earthquake waves by the soil medium. Since, as reported, the frequency of the soil medium or soil strata in Mexico City was quite close to the frequency, to predominant frequency of the earthquake ground motion, and most of the structures, building structures in Mexico City generally were 10 to 12 stories high, and therefore almost had the same frequency or natural frequency of free vibrations as the frequency of the earthquake and the soil medium. A phenomenon called double resonance occurred in the Mexico City, which was primarily responsible for the extensive and serious damage to the building structures, even though the Mexico City earthquake was classified as a moderate earthquake in terms of the peak ground acceleration. The third general parameter that determines the effect of this seismic ground excitation or the earthquake ground motion on the building structure, which we commonly refer to as the earthquake loading or the intensity of earthquake loading, is the earthquake ground motion itself that is the dynamic characteristics of the earthquake ground motion, in addition to the dynamic characteristics of the building structure, dynamic characteristics of the foundation soil medium, the dynamic characteristics of the earthquake ground motion, including the duration, the intensity, and the frequency content of the earthquake ground motion, also governs the dynamic response of the building structure to the earthquake ground motion, termed as the seismic response of the building structure. And the exercise of theoretically or numerically or computationally predicting the dynamic response of a building structure to an earthquake ground motion, termed as the seismic response of the building structure, subjected to an earthquake ground motion, mathematically represented as an acceleration function of time, acceleration time history, is termed as seismic analysis of the building structure. And based on the discussion of this slide so far, it is intuitive that the seismic response of the building structure, that is the dynamic response of the building structure to an earthquake ground motion, can be analytically or theoretically predicted by performing the seismic analysis of the building structure, that is the dynamic analysis of the building structure, given the dynamic characteristics of the building structure, the dynamic properties of the foundation soil medium, and the earthquake ground motion, represented as a time history of the earthquake ground acceleration. In general, the earthquake ground motion is modeled as an acceleration time history, that is a time varied function of acceleration measured at the level of the foundation of the building, and therefore given the ground acceleration time history, that is induced by an earthquake at the base of the structure, that is at the foundation of the building structure, the dynamic analysis of the building structure subjected to the earthquake ground motion with the ground accelerations time history provided at the level of the foundation or at the level of the base of the structure, therefore requires only the dynamic characteristics of the structure and the earthquake ground acceleration time history. Since the earthquake ground acceleration time history has been measured and quantified or recorded at the level of the foundation of the structure. So as far as the structural engineer is concerned, the nature of the dynamic characteristics of the foundation soil medium or the soil strata is not considered in the dynamic analysis of a building structure subjected to an earthquake ground motion that is modeled as an earthquake ground acceleration time history with the ground accelerations measured at the ground level, that is the foundation level, using accelerometers, for example, installed at the building site. Therefore, to conclude, the discussion presented in this slide, a few definitions will be pertinent and useful, or the definition of few standard or typical terms in the terminology of earthquake resistant design or seismic analysis. For example, seismic response is defined as the structural response of the building structure to an earthquake, and seismic analysis is defined as the numerical or computational or analytical task or exercise to theoretically predict the dynamic response of a building structure to an earthquake ground motion, which is termed as the seismic response of the building structure. Now, with that overview of the background on the seismology of earthquakes, that is the seismological factors that determine the intensity of the earthquake at any site of the building or earthquake, the mathematical modeling of an earthquake ground motion for the purposes of structural analysis of building structure, to determine the dynamic response of the building structure subjected to the earthquake, and the dynamic parameters or dynamic characteristics that govern the dynamic response of the building structure to the earthquake ground motion, termed as the seismic response of the building structure to an earthquake, or more commonly the earthquake loading. We will proceed to the principles and fundamentals of mechanics that can be applied to mathematically derive the code specified formulations for calculation of earthquake loads, prescribed by the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, that is IS 1893, Part 1, the 2016 revision, which is also the latest revision of the code. Once again, it is worthwhile to note that our endeavor will be to start from the first principles of mechanics or physics to arrive at the code specified, rather the theoretical basis of code specified formulations. And since the first principles of mechanics or physics that are relevant for mathematically deriving the theoretical basis of the code specified formulations for design earthquake loads, are in the scope of the theory of structural dynamics, that is the dynamics of structures, we will revisit or review some of the first principles of structural dynamics or theory of dynamics of structures that are relevant from the point of view of intuitively understanding the seismic response of building structures, that is, the structural behavior of building structures subjected to earthquakes. For the purposes of the structural analysis of building structures, to predict the dynamic response of such structures under the action of an earthquake, ground motion, also termed as the dynamic response of building structures to earthquakes, or in the terminology of earthquake resistant design or seismic design, termed as seismic. As we were discussing, the theoretical basis for mathematically deriving the code specified formulations for calculation of design earthquake loads as per the latest Indian seismic design code, that is the Indian Standard Code of Practice for earthquake resistant design of building structures, IS 1893 2016, the latest revision. One has to have an intuitive understanding and insight into the structural response of building structures to earthquake ground motions, termed as seismic response of building structures. And in order to gain an insight or an intuitive understanding of the seismic response of building structures, that is, the dynamic response of building structures subjected to earthquake ground motions, a brief review of the structural dynamics for single degree of freedoms is most useful and beneficial. With that objective in mind, a brief review of the theory of structural dynamics for single degree of freedom structural systems has been presented in the PDF file that is uploaded on the Impartus link of the Moodle website for the course. The students are encouraged to read and understand the brief overview of the theory of structural dynamics for single degree of freedom systems that has been published on the Impartus link of the Moodle website for the course, in order to intuitively understand the theoretical basis or the background theory for the code specified formulations for calculating earthquake loads as per the latest Indian seismic design code. Based on an overview of the theory of structural dynamics of single degree of freedom structural systems that has been uploaded on the Partis link of the Moodle website for the course, it is intuitive that the qualitative trends of the plot of the frequency response function, that is abbreviated as FRF, for a single degree of freedom mass spring dashpot oscillator considered as an analogy to the single story frame with the rigid floor mass, that is also a single degree of freedom system, shows a distinct resemblance with the design response spectrum that is provided by the latest Indian seismic design code, that is the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, in figure 2 of the 2016 or the latest revision of the Indian Seismic Design Code. And the design response spectra for a single degree of freedom single story frame model with the rigid floor mass, that is a single degree of freedom system, as presented in IS 1893 Part 1 2016, the latest revision of the Indian Seismic Design Code, is schematically illustrated in this figure. As you can observe from the figure, the design response spectrum provided by the latest Indian Seismic Design Code, IS 1893 Part 1 2016 revision, bears a very strong resemblance to the frequency response function, abbreviated as FRF, for the single degree of freedom SDOF mass spring dashpot oscillator, that is theoretically derived in the overview of the theory of structural dynamics for single degree of freedom systems for a single story frame model with rigid floor mass, that is a single degree of freedom system. And also uploaded on the Impartus link of the Moodle website for the course. Well, it is worthwhile to note that the resemblance of the design response spectrum provided by IS 1893 2016 revision, that is the latest revision of the Indian Seismic Design Code, in figure 2, to the frequency response function for the single degree of freedom SDOF mass spring dashpot oscillator, considered as an analogy to the single story frame model with the rigid floor mass, also a single degree of freedom system. Is not coincidental. The trends of the plot of the design response spectrum provided by the latest Indian Seismic Design Code resemble the trends of the frequency response function that has been derived for a single degree of freedom, abbreviated as SDOF mass spring dashpot oscillator system, considered as an analogy to the single story frame model with a rigid floor mass. Since the theoretical basis or the theory of structural dynamics underlying the frequency response function derived in the overview of theory of structural dynamics of single degree of freedom systems, published on the Moodle website, Impartus link, and the code specified response spectrum presented in figure 2 of the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, IS 1893 2016, reproduced in this figure. Are the same. Well, more importantly, the design response spectrum provided by the latest Indian Seismic Design Code IS 1893 2016 revision in figure 2 as reproduced here lends itself to a number of informative interpretations in terms of the physical understanding of the dynamic response of single story frame models with rigid floor mass as considered in the brief overview of theory of structural dynamics for single degree of freedom systems, or single degree of freedom building structures for which the design response spectrum has been generated and provided in figure 2 of IS 1893 2016. So proceeding to the physical interpretation of the dynamic response of single degree of freedom building structures to earthquake ground excitation as summarized by the figure 2 depicting the design response spectra. The design response spectra has been generated and provided in IS 1893 Part 1 2016 figure 2 as a plot of the normalized spectral or peak acceleration of the floor mass of the single degree of freedom mass spring dashboard system, which is the idealized analogy for a single degree of freedom building structure or a single story frame with a rigid floor mass as shown in the overview of the theory of structural dynamics of single degree of freedom structural systems uploaded on the Impartus link of the Moodle website. And the plot of the normalized spectral or peak acceleration of the floor mass is with respect to the natural period, that is the fundamental time period of the single degree of freedom building structure. It should be noted that the design response spectra presented in figure 2 of IS 1893 2016, the latest revision of the Indian Seismic Design Code, illustrates the plot of the normalized spectral or peak acceleration And by normalized, we mean the peak or the spectral acceleration of the floor mass divided by g, the acceleration due to gravity. That is, the peak or spectral acceleration normalized with respect to the acceleration due to gravity is plotted on the y-axis of the design response spectrum, presented in figure 2 of IS 1893 2016, while the x-axis represents the natural period or the fundamental time period of the idealized single degree of freedom structural system. One may note that this natural period or the fundamental time period is related to the circular frequency of the free vibrations by this relationship T is equal to 2 pi by omega, where the circular frequency omega of the free vibration response of the idealized single degree of freedom structural system, analogous to the single degree of freedom mass spring dashpot oscillator considered in the overview of theory of structural dynamics for single degree of freedom systems, is equal to the under root of the mass to the spring constant or spring stiffness of the analogous single degree of freedom mass spring dashpot oscillator. Therefore, based on the qualitative trends exhibited by the plots of the normalized spectral or peak acceleration divided by g for normalization, the acceleration due to gravity being the normalizing factor, with respect to the natural period or the fundamental time period of the idealized single degree of freedom structural system, larger the damping ratio corresponding to the natural or viscous damping of the system, lower are the spectral accelerations or peak accelerations in normalized terms. Physically, in terms of real or practical building structures, the damping ratio for steel structures is typically 3%, while the damping ratio for RC or reinforced concrete structures is typically 5%, and though that for brick masonry structures is 7%. As one can note from the design response spectra, larger the damping ratio that represents the viscous or natural damping in the building structure due to the friction between the molecules of the material being dependent on the material. Lower is the normalized spectral or peak acceleration, SA by G. More importantly, more important or physically significant trend that one can observe from the design response spectra presented in figure 2, the latest Indian seismic design code, that is IS 1893 2016 revision, is that larger the time period, that is, longer the natural period or the fundamental time period of the building structure, lower or lesser is the spectral or peak acceleration in normalized terms, as one can see from this declining curve for each damping ratio, that is xi equal to 3% for steel structures, xi equal to 5% for reinforced concrete structures, and psi, that is the damping ratio, representing the natural or viscous damping of the structure in percentage for brick masonry structures as 7%. Regardless of the damping ratio representing the natural or viscous damping corresponding to the construction material, the peak or spectral accelerations normalized with respect to g, the acceleration due to gravity, decrease in an exponential manner with increase in the time period, that is the natural period or the fundamental time period of the idealized single degree of freedom structural system. In fact, it is quite informative to consider two extreme scenarios or two extreme cases, that is the two extreme points of the design response spectrum. Well, on the left extreme point of the design response spectrum provided by the Indian Seismic Design Code IS 1893 2016 revision, we have the natural period or the fundamental time period of the building tending to 0, that is tending to extremely short time periods, which corresponds in physical terms to extremely stiff buildings as infinitesimally small time period tending to 0, in physical terms implies an infinite stiffness K, that is the left extreme of the design response spectrum corresponding to natural period T equal to 0 or tending to 0 pertains to extremely stiff buildings with the spring stiffness or spring constant K of the idealized singular degree of freedom structural system tending to infinity, and therefore the natural circular frequency tending to infinity, thus corresponding to extremely stiff systems that lie on the left extreme of the design response spectrum, for which the normalized spectral acceleration or peak acceleration has been provided as 1 corresponding to extremely stiff buildings with natural period or fundamental time period tending to 0. The physical interpretation of this trend in qualitative terms is that an extremely stiff building, for example, this rigid block that is a single story, depiction of a building deemed to be extremely stiff or rigid has a stiffness that is so large because of the rigidity of the block that the natural period or the fundamental time period of such an idealized rigid building structure, for example, the rigid single story block depicted in this figure, with a time period or natural period tending to 0. Therefore, for this rigid block depicting an extremely stiff building with the natural period or fundamental time period t tending to 0, the peak acceleration or spectral acceleration, which is a measure of the absolute acceleration of the building, that is the total acceleration of the building, is the same as the ground acceleration. The physical meaning of this trend, wherein an extremely stiff building depicted by a rigid single-story block shown in this figure with a time period that is extremely short and in the limit tending to 0, having the same peak or spectral acceleration as the earthquake ground acceleration, is that the rigid block that is the idealized depiction of the extremely stiff building simply follows the ground in the event of an earthquake. The rigid block that represents the idealized depiction of an extremely stiff. The rigid block that is exhibited on the left end of the design response spectrum shown in this figure schematically represents an extremely stiff building, that is a building with the natural circular frequency of the first mode of free vibration omega tending to infinity due to the infinitesimally large spring stiffness or the spring constant K of the building. This is the mass of the building, is a physical constant and therefore cannot be 0. In physical terms, an extremely stiff building on the left hand side of the response spectrum, for example, the single story rigid block depicted in this figure, on the left end of the design response spectrum corresponds to an extremely stiff building with the natural circular frequency of the first mode of free vibration omega tending to infinity due to the infinitely large stiffness or spring constant, that is spring stiffness K of the idealized singular degree of freedom structural system. Therefore, in case of such buildings that are extremely stiff with the natural period or the fundamental time period tending to 0 and thus lie on the left extreme of the design response spectrum, the peak or spectral acceleration has been prescribed in normalized terms, that is, the peak or spectral acceleration normalized by dividing with the acceleration due to gravity g has been prescribed as 1. The physical reasoning for this trend that can be noted from the design response spectrum presented in figure 2 of the Indian Seismic Design Code IS 1893 2016, the latest revision, is that an extremely stiff building with the natural period or the fundamental time period capital T tending to 0 due to physical reasoning of the stiffness or the spring constant or the spring stiffness K tending to infinity and the natural circular frequency of first mode of free vibration omega tending to infinity as might be observed in this rigid single story block depicted in this figure on the left end or the left extreme of the design response spectrum. In such extremely stiff buildings that are almost or infinitely rigid or stiff, as depicted by this rigid single story block lying on the left end of the spectrum at its left extreme, the building or the rigid block is so stiff or rigid that the building simply follows the ground in the event of an earthquake ground motion. In other words, such extremely stiff buildings as depicted by the rigid single-story block in this figure shown on the left extreme of the spectrum. Simply follow the earthquake ground motion. That is, if the ground moves to the left with a certain acceleration, the block moves along with the ground, and if the ground moves to the right with a certain earthquake ground acceleration, the rigid single-story block simply moves with the ground and follows the earthquake ground motion, and therefore the spectral acceleration or peak acceleration normalized with respect to the ground, with respect to the acceleration due to gravity, has been prescribed as one for such extremely stiff buildings with natural period or fundamental time period capital T tending to 0 due to the physical reason of the spring stiffness or spring constant or K tending to infinity. Now, it is equally interesting to derive physical interpretation or physical understanding of the seismic response of building structures that lie on the other extreme of the design response spectrum, that is, the extreme wherein the time period, that is the natural period or the fundamental time period capital T, tends to infinity. Now, in case of such building structures, wherein the natural period or the fundamental time period capital T tends to infinity, and the physical relevance or physical significance of an infinitely large natural period or fundamental time period T is that the idealized single degree of freedom structural system corresponding to the building structure has an extremely small spring stiffness or spring constant K that is tending to 0, and therefore natural circular frequency of free vibration omega also tending to 0, as in case of extremely flexible structures in reality. For example, a 40-story building structure that approximately displays a natural period or fundamental time period of free vibration in the first mode as 4 seconds depicts an example of an extremely physical structure that lies on the other end or the other extreme of the design response spectrum as shown in this figure. In other words, in case of extremely flexible structures with the spring stiffness or spring constant K of the idealized single degree of freedom structural system tending to zero, and therefore the natural frequency omega, natural circular frequency omega of the first mode of free vibration of the building tending to zero. The natural period or the fundamental time period denoted as capital T tends to infinity, and in case of such extremely flexible structures with extremely long time periods, for example, this 40-story building frame depicted in this figure on the right end or the right extreme of the design response spectrum, estimated to have a natural period or fundamental time period T of approximately 4 seconds. The spectral acceleration or the peak acceleration normalized with respect to the acceleration due to gravity, that is SA by G, is extremely small, and the physical reasoning for extremely small or low normalized spectral or peak acceleration for such extremely stiff, extremely flexible building structures such as the one depicted by this 40-story building frame shown in this figure on the right hand extreme of the design response spectrum. Are so flexible because of the extremely long time period or extremely small natural circular frequency of free vibration or extremely small stiffness or spring constant K, that the mass does not move at all with the ground in case of an earthquake ground motion. An interesting analogy that can be presented to illustrate the dynamic response of such extremely flexible structures, for example, the 40-story building structure or building frame that is 40-story high, depicted in this figure shown on the right hand extreme of the design response spectrum. when subjected to an earthquake, ground motion can be considered analogous to a balloon on a string, since the string has negligible stiffness that can be considered as tending to zero, and therefore the natural circular frequency or the free vibration in the first mode of this balloon on a string system can be visualized to be tending to zero, and thus the time period, that is the natural period of the free vibration response of this balloon on a string system, or the fundamental time period corresponding to the first mode of the free vibration response of this balloon on a string system, can be visualized to be tending to infinity, as in case of such extremely flexible systems, the time taken for the structure or the single degree of freedom system to complete one vibration, to complete a single vibration and return to the equilibrium position when disturbed or displaced from its equilibrium position. For example, highly or extremely flexible 40-story building frame, when displaced from its equilibrium position, will take a long time to complete one full cycle of oscillation, as in case of this analogous balloon on a string system, which, if displaced from its equilibrium configuration, will take a long time to complete one full cycle of oscillation, thus exhibiting a long, extremely long time period, t tending to infinity. Now, in case of such extremely flexible structures, for example, the 40-story building frame that is depicted on the right hand extreme of this design response spectrum, and as explained using the physical analogy of a balloon on a string system displayed in this figure, the normalized spectral acceleration or peak acceleration of such extremely flexible structures is extremely low, as displayed by the trend qualitatively of the design response spectrum for large or extremely long natural periods or fundamental time periods T. The physical explanation of the observation, that is low or extremely small spectral accelerations or peak accelerations normalized with respect to G, that is SA by G, as exhibited by the design response spectrum for extremely flexible structures on the other extreme of the design response spectrum, that is in the limit of natural period or fundamental time period T tending to infinity, is that in case of such extremely flexible systems wherein the spring stiffness or spring constant K of the idealized single degree of freedom structural system can be assumed to be tending to zero, and therefore the natural circular frequency omega tending to zero, and thus the natural period of the fundamental time period T tending to infinity, the mass does not move at all in the event of an earthquake ground motion. Even if the ground moves as depicted in this balloon on a string system, even if the ground moves from left to right and left to right due to earthquake ground motion, the balloon remains more or less in its equilibrium position, since the string is extremely flexible and therefore has a negligible spring stiffness or spring constant K that is tending to zero, thus resulting in an infinitely large or long time period T for the balloon on string system. In case of the extremely flexible 40-story building frame, the building structure is an extremely flexible structural system with a spring constant K of the idealized single degree of freedom structural system tending to zero, and thus the natural period or the fundamental time period capital T of the building structure tending to infinity, and physically visualizing the dynamic response of such a extremely flexible building structure such as the 40-story building frame depicted on the right hand extreme of this design response spectrum. The frame or the building structure does not move even though the ground moves due to the earthquake ground excitation. The building frame that is extremely flexible, for example, the 40-story building frame exhibited on the right hand side of the spectrum, does not exhibit any significant motion because of its extreme flexibility or extremely long time period, as in case of this balloon on a string system. Even though the ground vibrates or moves due to the earthquake ground motion. And as a result, the total acceleration or the peak or spectral acceleration of the extremely flexible structures such as the 40-story building frame shown on the right hand extreme of this design response spectrum, and the analogous balloon on a string system also shown on the right hand extreme of this design response spectrum. Continuing our discussion on the theoretical basis or the background theory underlying the code specified equations for calculating the design earthquake loads, as prescribed by the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, that is IS 1893 Part 1, 2016, or the latest revision. The mathematical derivation of the code specified formulations for calculating design earthquake loads can be completed by starting from the first principles of the theory of structural dynamics, that is, the fundamentals of dynamics of structures, to arrive at the code specified formulations for calculating the design horizontal seismic force specified in the form of the design horizontal seismic base shear, denoted as V subscript B. The symbol V signifies the shear force acting at the base of the building structure that is to be considered for the design of the building structure under the action of the earthquake loads, while the subscript B denotes the base shear, that is, the design horizontal seismic base shear, which is also equal to the total lateral earthquake force or the total horizontal seismic force acting on the building structure, as one can verify by considering the free body diagram of the entire building structure. Therefore, the response spectrum method of seismic analysis, that is specified by IS 1893-2016, the Indian Standard Code of Practice for Earthquake Resistant Design of building structures provides the design formulation for calculating the design horizontal seismic base shear VB as per clause 7 of IS 1893, and the design horizontal seismic base shear is computed using this formulation presented on this slide right here. And our objective today in the present discussion is to derive the theoretical basis of the court specified formulation for the design horizontal seismic base shear as provided by clause 7 for the application of the response spectrum method of seismic analysis. Recall that seismic analysis is the exercise of calculating the design earthquake loads or the design seismic forces acting on the building structure for the purposes of the structural analysis of the building structure to determine the seismic response of the building structure, that is the dynamic response of the building structure subjected to earthquake loading. So, as mentioned earlier, beginning from the first principles of the theory of structural dynamics or the fundamentals of dynamics of structures, considering this single story frame model with a rigid floor mass M as highlighted by this shaded block that represents the rigid floor mass with the value of the mass as capital M. If we consider the free body diagram of the rigid floor mass in this single story frame model, that is a single degree of freedom structural system, the most elementary example of a building structure with a single degree of freedom, that is the displacement u in the x direction, which is time variant in general, since the dynamics of the structure are of interest, that is, we are interested in the dynamic response of the single degree of freedom frame model. Therefore, designating the single and the only degree of freedom, that is the lateral or the horizontal displacement along the x direction of the floor mass M, denoted as u, where u is a function of time or is a time variant function in the general case of the dynamics, or the general case wherein the dynamic response of the single story frame model is of interest. Thus, uh, noting that the only single degree of freedom, that is the only displacement of the single degree of freedom single story frame model illustrated in this figure, is the displacement u as a function of the time t with respect to the ground, that is the frame of reference. Note that the free body diagram of the floor mass m circumscribed by this green ellipse right here can provide the basis for the mathematical derivation of the dynamic equilibrium equation of the single story frame model. Therefore, considering the free body diagram or the free body FBD of the floor mass in this single story, single degree of freedom frame model, the theoretical basis for the mathematical derivation of the dynamic equilibrium equation of the floor mass can be written using the Newton's second law of motion, and the dynamic equilibrium of the free body of the rigid floor mass FBD, highlighted and circumscribed by the green ellipse right here, may be expressed by the following dynamic force equilibrium equation. The equilibrium equation is termed as dynamic since time variant functions of the various forces acting on the free body are considered. That is, the forces considered acting on the free body of the floor mass are functions of time. Therefore, the force equilibrium equation that is written for the free body of the rigid floor mass M is a dynamic force equilibrium equation where the first term is the inertial force denoted as F subscript I, where the subscript I signifies inertia or the inertial nature of the force that is acting on the rigid floor mass M due to the inertia of the floor mass M when subjected to an earthquake ground motion, that is earthquake or seismic base excitation at the base of the single story frame model. In other words, the the floor mass m, circumscribed by this green ellipse, experiences an inertial force denoted as F subscript I, a time variant function. Due to the inertia of the floor mass under the action of an earthquake ground motion, that is represented or modeled as an earthquake ground acceleration time history, depicted by this red signal, or red disturbance, or red external disturbance, or external forcing function, or an external ground acceleration time history depicted in red ink and termed as U double dot subscript G, also a time variant function. Therefore, considering the dynamic equilibrium of the rigid floor mass m, idealized as a free body FBD circumscribed by the green ellipse, under the action of an earthquake ground acceleration time history, or a seismic ground motion time history expressed as an acceleration time history denoted as U double dot subscript G as a function of time, with the subscript G signifying ground, signifying that the acceleration time history is that for the ground and is acting at the base of the single story frame model, that is at the level of the ground G. The other dynamic forces, in addition to the inertial force that is experienced by the floor mass due to the inertia by the virtue of Newton's second law of motion, denoted as the inertial force, termed as the inertial force, denoted as F subscript I, as a function of time, or time variant function of the inertial force that is experienced by the floor mass by virtue of its inertia against the motion imparted by the earthquake ground excitation, or the seismic base excitation, as represented by the earthquake ground acceleration time history depicted in red ink and denoted as U double dot G, with the argument T, that is the earthquake ground acceleration is modeled as an earthquake ground acceleration, time history, or time variant function. The other dynamic forces under which the free body diagram of the floor mass is in equilibrium, in addition to the inertial force F subscript I, are the damping force denoted as F subscript D, where the subscript D signifies damping, or that is the viscous or the natural damping of the single story frame, specifically the viscous or natural damping of the columns of the single story frame, and is symbolically represented by this dash pot, the traditional symbol of the dash pot shown in the figure represents the natural or viscous damping of the single story frame model, which induces a time variant damping force that is denoted as F subscript T, also a function of time, and acting in the direction opposite to the earthquake ground motion, and as well as the relative displacement or the only single degree of freedom of the single story frame model, that is U. Additionally, the floor mass is also subjected to the spring force denoted as Fs, where S subscript S signifies the spring, that is the spring or the stiffness of the single story frame model in the horizontal or lateral direction. And since the stiffness is traditionally represented by spring, the spring stiffness of the two columns of the single story frame model is K, that is the combined spring stiffness in the horizontal or lateral direction of the two columns or both the columns together is K, assuming that each column has an equal spring stiffness with the spring constant equal to K by 2 for each column, thus resulting in a total combined lateral or horizontal spring stiffness of K for both the columns. So, the dynamic equilibrium of the rigid floor mass considered as a free body is under the action of three fundamentally different types of dynamic forces: the inertial force denoted as F subscript I, the damping force denoted as F subscript T, and the spring force denoted as F subscript S, each one of which are expressed as time variant functions or functions of time, since the dynamic equilibrium or the dynamic response of the single story frame model is of interest in the present scenario. Now, substituting the individual magnitudes of the three different dynamic forces under which the floor mass M is in dynamic equilibrium, the inertial force Fi can be written as the mass times the total acceleration in the horizontal direction of the floor mass that is considered as the free body, circumscribed by this green ellipse. Now note that the total acceleration is denoted as u double dot subscript total, and represents or equals the absolute acceleration of the floor mass M considered as the free body. The reason that the subscript total or the notation for the acceleration of the floor mass is adopted as u double dot subscript total is that the ground, which is the frame of reference for measuring the relative displacement u in the horizontal direction of the floor mass M, is not stationary, that is not at rest, but is also subjected to a motion, that is the earthquake ground motion, represented or modeled by an earthquake ground acceleration time history. Therefore, as a result of the earthquake ground motion, the ground itself cannot be considered as an inertial frame of reference, as the ground, when considered as a frame of reference, is not at rest and therefore not a stationary or inertial frame of reference. Therefore, the inertial frame of reference will have to be a frame of reference that is at rest and therefore can qualify as an inertial frame of reference for applying the Newton's second law of motion. Now, a point on the Earth's surface, or for example, a point within the Earth's surface or on the Earth's surface, for example, the center of the Earth, may be considered as an inertial, as the origin for an inertial frame of reference, or any point on the Earth's surface that is not affected or not subjected to the earthquake ground motion, because by being very distant or far from the earthquake site. So any point on the Earth's surface or within the Earth's surface that is not subjected to earthquake ground motion, or that is not in motion, that is not accelerating specifically. For example, the center of the Earth, or a point on the Earth's surface that is not affected by the earthquake ground motion and is therefore not accelerating, can be adopted as the inertial frame of reference. Since the definition of an inertial frame of reference for the application of Newton's second law is a frame of reference that is not accelerating, since the ground at the building site or the earthquake site is subjected to earthquake ground acceleration. The ground itself does not qualify as an inertial frame of reference, and therefore, for purposes of applying the Newton's second law, we consider a point the distant from the earthquake site or the building site that is not subjected to earthquake ground acceleration and therefore qualifies as the origin for an inertial frame of reference, provided the point or the origin is not accelerating for any reason. Therefore, considering an inertial frame of reference with the origin at a point that is not subjected to earthquake ground acceleration because of the distance from the earthquake site and is not accelerating due to any other reason, the inertial force can be expressed as the inertial force acting on the rigid floor mass m, considered as the free body, can be written as mass m times the total acceleration or the absolute acceleration of the floor mass, denoted as u double dot subscript total, where the subscript total signifies the absolute acceleration. Obviously, a time variant function, since the total acceleration or the absolute acceleration of the floor mass with respect to the inertial frame of reference is also a function of time. The second dynamic force, that is the damping force, also a time variant function, denoted as Fd with subscript d signifying damping and the argument t signifying that the damping force F subscript d is a function of time, is given as the damping constant or the damping coefficient C times the relative velocity or the relative speed u single dot as a function of time of the floor mass with respect to the ground. So substituting the formulation for the damping force F subscript D given as the damping constant C times the relative velocity of the floor mass in the horizontal direction, denoted as u single dot t, a time variant function, in the x direction or the direction of the only and the single degree of freedom, that is the displacement u. Well, it should be apparent that u single dot t is the first derivative of u, or the relative displacement, expressed as a function of time or time variant function, while u double dot t, that is the relative acceleration of the floor mass in the horizontal direction or the x direction, is the second derivative of the relative displacement u with respect to time, where u, a time variant function of t, is the relative displacement of the floor mass, the only single degree of freedom, that is the displacement of the floor mass relative to the ground in the direction of the single degree of freedom of the single story frame model. Now with that, theoretical formulation for the dynamic damping force denoted as F subscript D, we proceed to the theoretical formulation for the dynamic spring force denoted as F subscript S, and it's well known relationship for the spring force is simply the spring constant K, or the spring stiffness K, which in this case is the combined spring stiffness of the two columns of the single story frame model together times the relative displacement of the floor mass relative to the ground, thus resulting in the dynamic spring force, since the relative displacement itself is time variant function, dynamic quantity. The spring force resulting from the multiplication of the spring constant or spring stiffness K and the relative displacement is also a dynamic quantity. Substituting the formulation for the spring force in the equilibrium, in the dynamic equilibrium equation, the theoretical formulation for the dynamic equilibrium equation of the rigid floor mass considered as the free body diagram highlighted by or circumscribed by the green ellipse as shown in the figure of the single story frame model, may be expressed as mass times the total acceleration, that is mass m times the total or the absolute acceleration of the floor mass u double dot subscript total plus the damping constant c times the relative velocity of the floor mass with respect to the ground plus the spring constant or spring stiffness K times the relative displacement of the floor mass with respect to the ground, which is the only displacement or the only and the single degree of freedom of the single story frame model shown in this figure. And the sum of three dynamic quantities, that is the dynamic inertial force, the dynamic damping force, and the dynamic spring force, all the three expressed as functions of time, or time variant functions, should equal 0 for the free body to be in dynamic equilibrium. The prefix dynamic signifies that the equilibrium being considered is in motion, equilibrium for the motion of the floor mass, that is the dynamic equilibrium. And since the floor mass is in motion and is not at rest, the prefix dynamic is being used in this discussion to highlight that the equilibrium is dynamic and not static equilibrium that we are considering. In other words, the equilibrium equation derived in this slide is the dynamic equilibrium equation of the floor mass m, since floor mass m is in motion and not at rest. Well, after completing the derivation of the dynamic equilibrium equation of the rigid floor mass considered as free body, we can rearrange the terms, noting that the second two terms, that is the sum of the dynamic damping force and the dynamic spring force, together constitute the base shear, that is the dynamic damping force F subscript D and the dynamic spring force F subscript S, together constitute the base shear VB, or the theoretical base shear V subscript small b. The subscript small b is used in the theoretical formulation to highlight that the base shear V subscript B, that is V subscript small b, is the theoretical base shear that is obtained theoretically by considering the dynamic equilibrium of the free body diagram of the rigid floor mass. Recall that the notation V subscript large b was used to represent the design horizontal seismic base shear that is provided by the IS code, and the subscript large b in the notation V subscript large b signifies that the base shear is the parameter V subscript large b is the design horizontal seismic base shear that is calculated as per the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, that is IS 1893 2016. Returning to the theoretical formulation, that is the mathematical derivation of the theoretical basis for the code specified design earthquake loads, proceeding with the dynamic equilibrium equation derived mathematically by considering the dynamic equilibrium of the free body of the rigid floor mass circumscribed by the green ellipse. Noting that the second and third terms in the dynamic equilibrium equation thus derived, which are the terms corresponding to the dynamic damping force and the dynamic spring force, together constitute or equal the dynamic base shear, that is, the dynamic shear force at the base of the single story frame model. When we consider the free body of the entire single story frame, one can verify that the theoretical dynamic base shear V subscript small b, a time variant function, is equal to the sum of the dynamic damping force F subscript D and the dynamic spring force F subscript S, both of which are also time variant. So recognizing the sum of the latter two terms, the second and third terms, corresponding to the dynamic damping force and the dynamic spring force in the dynamic equilibrium equation, constitute the theoretical dynamic base shear, also a function of time or a time variant function. One can rearrange the terms in the dynamic equilibrium equation derived as shown here to write the formulation, the theoretical formulation for the theoretical dynamic base shear V subscript small b with argument t, signifying that the theoretical dynamic base shear V subscript small b is a time variant function or a dynamic quantity, which by rearranging the terms in the dynamic equilibrium equation thus derived can be expressed as the sum of the dynamic damping force, that is C times U single dot T, plus the dynamic spring force, that is K times U of T. And rearranging the terms in the dynamic equilibrium equation shown here, the sum of these two terms corresponding to the dynamic damping force and the dynamic spring force together equal the theoretical dynamic base shear V subscript small b, a time variant or function. And each of these are equal to minus or negative of the mass times the total acceleration u double dot total, the notation for the total or absolute acceleration of the floor mass times the mass m, that is the value of the mass of the floor denoted as small m, represents the inertial force, and one can rearrange the terms in the dynamic equilibrium equation, taking the term corresponding to the dynamic inertial force F subscript I, that is equal to m u double dot total as function of time to the other side, that is the right hand side of the equation, for the dynamic equilibrium of the floor mass. The theoretical dynamic base shear V subscript small b, a time variant function that is related to the dynamic damping force F subscript D and the dynamic spring force F subscript S as the theoretical dynamic base shear is equal and opposite to the sum of the dynamic damping force and the dynamic spring force. Therefore, the theoretical dynamic base shear V subscript small b, time variant function, can be related to the inertial force, the dynamic inertial force, that is the mass times u double dot total acceleration, that is mass times the total or the absolute acceleration of the floor mass, by rearranging the terms in the dynamic equilibrium equation, taking the term corresponding to the dynamic inertial force to the right hand side, the theoretical dynamic base shear V subscript small b as a function of time is shown to be equal to minus of the mass m times u double dot subscript total, that is the theoretical dynamic base shear can be shown to be minus or negative of mass times the total or absolute acceleration of the floor mass. Since for purposes of design only the peak values or the maximum values are of interest, the maximum of the theoretical dynamic base shear or the peak value of the theoretical dynamic base shear V subscript small b should therefore be considered to be equal to the maximum or the peak value of the right hand side, that is the dynamic inertial force given as mass times the total acceleration. To summarize, therefore, the theoretical formulation based on considerations of dynamic equilibrium, the design or the peak or the maximum values of the theoretical dynamic base shear V subscript small b can be derived mathematically as equal to the maximum or the peak value of the mass times the mass m times the total acceleration of the floor mass. Starting from first principles of the theory of dynamics and dynamic equilibrium of rigid bodies, that is, one can mathematically prove that the peak or the maximum value of the theoretical dynamic base shear V subscript small v for purposes of design is measured as the maximum or peak value of mass m times the total acceleration or the absolute acceleration of the floor mass m for the purposes of earthquake resistant design of this single story, single degree of freedom frame model. Comparing this theoretically derived equation for the peak or the maximum value of the theoretical dynamic base shear V under subscript small v, time variant function, to the code specified formulation for the horizontal seismic base shear, that is the design horizontal seismic base shear or the design horizontal earthquake force provided in the form of the design horizontal seismic base shear P subscript large p as the notation. The theoretical formulation, the theoretically or mathematically derived formulation given by equation 2 for the peak or the maximum value of the theoretical dynamic base shear V subscript small b is immediately comparable to the code specified formulation for the design horizontal seismic base shear denoted as V subscript large b provided in this equation number 1. Noting that the terms or the factors zi over 2r are essentially scaling factors or coefficients that are used to scale the design horizontal seismic base shear to account for the variations in seismicity or seismic activity between different regions in which the building site may be located, as well as the importance of the building and the ductility or the ductility capacity of the building depending on the material, form, size and type of the construction. So recognizing that these bunch of factors zi over 2r are essentially scaling factors and clubbing the scaling factors zi over 2r as a single coefficient, say termed as coefficient written in yellow ink, the design horizontal seismic base shear provided by the IS code or the code specified formulation denoted as V subscript large b can essentially be expressed as the coefficient times the weight divided by the acceleration due to gravity times the spectral or the peak acceleration provided by the response spectrum or the figure 2 of the Indian Seismic Design Code IS 1893. Noting that the ratio W over G represents the mass of the building, total mass of the building, denoted as M, the code specified formulation for the design horizontal seismic base shear denoted as V subscript capital B can be expressed as the product of the coefficients times the mass of the building times the spectral. Well, after completing the mathematical derivation for the theoretical basis of the code specified formulation for design earthquake loads as specified by the Indian Standard Code of Practice for Earthquake Resistant Design of Building Structures, that is IS 1893 2016, or the latest revision, we will now proceed to the mathematical derivation of the theoretical basis for the code specified design formulations or design criteria for wind loads. That is the mathematical derivation of the code specified design formulations for the design wind loads as specified by the Indian Standard Code of Practice for calculating design wind loads, that is IS 875 part 3, the latest 2015 revision. Recall that in the previous slide we had mathematically derived the theoretical basis for the code specified design horizontal seismic base shear, that is the design horizontal or lateral earthquake force, starting from the first principles of the theory of structural dynamics or the fundamentals of dynamics of structures. We had mathematically derived the theoretical equation or the theoretical formulation for the maximum or the peak value of the theoretical dynamic seismic base shear, V subscript small b, expressed as a function of time, based on the dynamic equilibrium equation formulated for a single story frame model with a single degree of freedom. Considering the dynamic equilibrium of a free body of the floor mass of the single story frame model and the theoretical equation or the theoretical formulation that we derived mathematically, starting from the first principles of theory of structural dynamics for the horizontal or lateral theoretical base shear V subscript small b, that was obtained or presented as equation number 2, could be interpreted, or is rather the theoretical basis for the code specified design formulation for the horizontal seismic base shear specified by the Indian Standard Code of Practice for earthquake resistant design of building structures, and denoted as V subscript capital B, as presented in equation number 1. So comparing equations number 2 for the theoretical dynamic horizontal seismic base shear V subscript small b, expressed as a function of time, that is presented by equation number 2, with the code specified design formulation for the design horizontal seismic base shear presented by equation number 1, as specified by the Indian Standard Code of Practice for earthquake resistant design of building structures. One can immediately interpret that the theoretical formulation for the theoretical dynamic base shear V subscript small b as a function of time is the theoretical basis for the code specified design formulation that is provided by equation number 1, for the design horizontal seismic base shear V subscript capital B as a function of time. Well, in the present slide today we will proceed along similar lines to mathematically derive the code specified design formulations for the design wind loads as specified by the Indian Standard Code of Practice for calculation of wind loads, that is IS 875 Part 3 2015 or the latest revisions, starting from the first principles of mechanics or physics, that is the fundamentals of fluid mechanics specifically, for the purposes of illustrating the mathematical derivation of the theoretical basis of the code specified design criteria for the wind loads. In case of wind loading, since wind is air or a fluid in motion, due to the terrestrial thermal gradient, or as well as the rotation of the earth about its axis, the theoretical basis for the code specified design criteria for wind loads should be found in the first principles or the fundamentals of fluid mechanics, since wind is air or fluid in motion relative to the earth's surface. One should attempt to derive the theoretical basis for the code specified design criteria for wind loads acting on building structures by starting from the first principles of fluid mechanics, that is the fundamentals of fluid mechanics, and then perhaps the boundary layer flow at a later stage. Therefore, as in case of the mathematical derivation of the theoretical basis for the code specified design formulations for earthquake loads, we will commence the exercise of mathematically deriving the theoretical basis for the code specified design criteria for wind loads, starting with the first principles or reviewing the fundamentals of fluid mechanics. Now recall, based on your first year course content of the first year course on fluid mechanics as well as hydraulics. The fundamentals of fluid mechanics provide the underlying theoretical basis for the physical interpretation of the code specified formulations for the design wind loads specified by the Indian Standard Code of Practice for calculating wind loads, that is IS 875 Part 3 2015, or the latest revision. Therefore, the mathematical derivation of the code specified design formulations for design wind loads should rationally and logically be initiated from the first principles of fluid mechanics, that is the concept of the drag and lift on bluff bodies obstructing a streamlined flow of fluid. Since wind is air or fluid in motion relative to the Earth's surface, the mathematical derivation of the code specified formulations starting from the first principles of fluid mechanics, may be initiated from the theory of, rather the fundamentals of the streamlined flow of fluids. And as you may recall, wind, that is air or fluid in motion, as in case of any fluid in a streamlined flow, exerts static forces in the along wind as well as the crosswind directions due to the drag and lift that are known to act on an obstruction to a streamlined flow of fluid, for example, air. Further recall, based on the fundamentals of fluid mechanics and streamlined flow of fluid, the drag or lift on a single stationary bluff body, for example this cylinder whose cross section is shown in this figure as the shaded yellow circle, is calculated using the following theoretical relation, that is, the drag or lift force F subscript D or L as applicable for drag or lift on any single stationary bluff body obstructing a streamlined flow of fluid, illustrated in this figure by the blue curves that represent the streamlines in a streamlined or laminar flow of fluid around a cylindrical bluff body. The drag or lift force F subscript D or L as applicable for drag or lift on this cylindrical bluff body, or simply a cylinder obstructing the flow of the streamlined or laminar flow of a fluid, with the streamlines represented or depicted as the blue curves with the arrows pointing in the direction of the streamlined flow, is calculated as half of the drag coefficient, denoted as C subscript D, or the lift coefficient, denoted as C subscript L. The subscripts D or L are applicable for drag and lift forces respectively. So the respective drag or lift coefficient, that is C subscript D or C subscript L, may be implemented in the theoretical equation for the drag or the lift force acting on the bluff body as applicable. So times the fluid density in the context of the wind, since air is the fluid in motion, the air density, that is rho subscript A, the notation for air density, times the square of the air speed or the wind speed or the speed of the fluid in a streamlined flow, times the normal area, that is the area of the bluff body projected normal to the direction of the fluid, or normal to the direction of the streamlined flow of fluid. Therefore, summarizing the basic concept from the first principles of fluid mechanics that provide the theoretical basis for the mathematical derivation of the court-specified design criteria for design wind loads. The drag or lift force Fd or L, F subscript D or L as applicable for drag or lift, acting on a single stationary bluff body, for example, cylinder in a streamlined or laminar flow of fluid, wherein the cylinder may be visualized as a building in a field of air flow or wind flow with a circular or cylindrical cross section. In the context of wind loading, the cylinder depicted by the shaded yellow circle may be visualized as a building with a circular cross section, a circular plan shape, in field of airflow, air being the fluid in the context of wind loading. So therefore, continuing with the first principles of fluid mechanics, or the concept of the theoretical equation based on the fundamentals of fluid mechanics for the drag or lift force acting on a single stationary bluff body obstructing a streamlined flow of fluid may be calculated or obtained using the fundamental relationship provided in equation number 1 based on the first principles of fluid mechanics. That is, the drag or lift force F subscript D or L as applicable is half of the drag or lift coefficient denoted as C subscript D or L as applicable times the air density, air being the fluid in motion in the context of wind loading, times the square of the air speed or the wind speed, since wind or air is the fluid in motion in the context of wind loads, times the area of the bluff body projected normal to the direction of the flow of fluid in the context of wind load acting on a cylindrical building. The area subscript A subscript normal notation would represent or signify the area of the building with a cylindrical shape or circular plan shape projected normal to the direction of the wind flow. So starting from these first principles of fluid mechanics and fundamental equations for the drag or lift force acting on single stationary bluff body obstructing a streamlined flow of fluid, our endeavor will be to obtain or derive mathematically the theoretical basis for the court specified design formulations for design wind loads as provided by the Indian Standard Code of Practice for calculating wind loads on building structures, that is IS 875 Part 3, the 2015 or latest revision. Continuing with our discussion on the theoretical basis for mathematical derivation of the court-specified formulations for calculation of design wind loads as specified by IS 875 Part 3, the latest 2015 revision, the Indian Standard Code of Design Practice for calculating wind loads on building structures. We will first have a brief review of the background theory on wind engineering, that is a specialized area that deals with the calculation or theoretical modeling of wind pressures and wind forces acting on building structures. Well, wind engineering is a very broad area. It's an area of study in itself. However, as structural engineers, the topics in the area of wind engineering that are of direct interest to us for calculation of the wind pressures and the resultant wind forces acting on building structures are the topics that are also common or overlapping with the fundamentals of fluid mechanics and boundary layer flow. That provide the theoretical basis for calculating the wind pressures and wind forces acting on building structures. So, proceeding with these common or overlapping topics in wind engineering that are referred for mathematical derivation of the court-specified formulations for calculating the design wind loads acting on building structures as specified by the Indian Standard Code of Design Practice for calculating wind loads, IS 875 Part 3, 2015 or latest revision. As structural engineers, we are concerned only with the background theory or the theoretical formulations that are relevant for calculation of the wind pressures and therefore the resultant wind forces acting on the building structures. Nevertheless, it is useful and advantageous to have a brief review of the relevant or overlapping or common topics in wind engineering. Briefly, in order to understand or physically interpret the mechanism or the mechanics involved in the action of wind pressures and resultant wind forces on building structures. Therefore, from the point of view of an introduction to the common or overlapping topics in wind engineering, we will begin with a brief overview of some definitions and concepts in wind engineering that will be useful and advantageous in understanding the physical significance of the court specified formulations for calculating the design wind pressures and design wind forces on building structures. Now, as a definition, wind is air that is essentially a fluid in motion relative to the Earth's surface that is induced by the terrestrial gradient as well as the rotation of the Earth about its own axis. The horizontal component of the atmospheric motion is generally termed as the wind, since the vertical component is largely negligible. Therefore, from the point of view of a structural engineer, for the purposes of calculating the design wind pressures and the resultant wind forces or force resultants of the wind pressure, the horizontal component of the atmospheric motion is only significant and is generally termed as the wind in the context of wind loading acting on building structures, since the vertical component is negligible in general in comparison to the horizontal component of the atmospheric motion or the horizontal component of the fluid motion or air in motion. Speed of the wind, that is air, essentially a fluid in motion, typically increases from zero at the ground, that can be considered as a boundary in a boundary layer flow, to a maximum value denoted as Umax, for example, at a height termed as the gradient height, generally denoted as H subscript small g, due to the boundary layer effect. And the mathematical modeling of the wind speed, that is speed of the air or fluid in motion in a boundary layer generally is based on the principles or fundamentals of boundary layer flow. There is a marginal variation in the wind direction with height from the boundary denoted as Z, a phenomenon that is termed as Ekman's effect. However, since the variation in the wind direction with height is marginal or marginally low, the Ekman's effect or the phenomenon that accounts for the variation in the wind direction is generally ignored in the mathematical modeling of the wind speed or the speed of the air or fluid in motion in the atmospheric boundary layer. Now, it is intuitive that wind, being air or essentially a fluid in motion in the atmospheric boundary layer with the Earth's surface or the ground, that is the terrain of the ground, being the boundary, is a boundary layer effect. The theoretical formulations that are generally implemented or formulated to represent or predict the speed of the fluid in a boundary layer should be applicable for modeling the wind speed, which is essentially air or fluid in motion in the atmospheric boundary layer. Therefore, the wind speed at any height Z above the ground, that is the boundary of the atmospheric boundary layer in the context of the wind flow, wind being air or fluid in motion in the atmospheric boundary layer can be calculated using the classical or traditional boundary layer equation, polynomial equation that should be familiar to everyone from the basic course content taught in the first year undergraduate course on hydraulics or fluid mechanics, and based on the boundary layer equation governing the wind speed or the speed of fluid in flowing in a boundary layer in the context of the wind, the boundary being the ground or the terrain, while the fluid being the wind or the air, may be theoretically obtained as the wind speed at a reference height that is available from experimental measurements, say u at the height z0 in the boundary layer, where z0 is the reference height at which the speed of the fluid or wind or air is available from measurements using instruments for measuring the speed of the fluid. In case of wind, the instruments that are used for measuring the wind speed in the atmospheric boundary layer at any reference height, denoted as Z0, are the anemometers, anemographs that are generally installed at the reference height Z0 above the ground, which is the boundary in case of the boundary layer flow of the wind. That is usually 10 meters above the mean ground level, abbreviated as MGL. Therefore, given the wind speed recorded by the wind speed measuring instruments termed as anemometers that are typically installed at a reference height Z0 above the ground or the boundary, with the reference height Z0 generally adopted as 10 meters as an international standard above the mean ground level, MGL. The wind speed at any other height in the atmospheric boundary layer of the wind, that is essentially a fluid, or air in motion, can be calculated using the traditional boundary layer equation. In the boundary layer equation that is presented here, the parameter alpha needs further explanation. Parameter alpha is termed as the surface roughness coefficient that accounts for the roughness of the surface of the boundary in the boundary layer flow. In the context of wind, that is essentially air or fluid in motion in a boundary layer, that is the atmospheric boundary layer above the ground, with the ground being the boundary of the atmospheric boundary layer. The parameter alpha, termed as the surface roughness coefficient, is based on the surface roughness of the ground, that is the boundary in the atmospheric boundary layer, and is dependent on the terrain conditions in the context of the wind in the atmospheric boundary layer. So the surface roughness coefficient alpha in the context of the atmospheric boundary layer would be adopted considering the terrain conditions of the boundary. In the context of wind flow, the boundary is the ground, and therefore the parameter termed as the surface roughness coefficient, denoted as alpha, will be dictated by the terrain conditions of the ground. The wind speed at any given height denoted as u, designated as a function of the height z above the mean ground level, in itself is a highly probabilistic, that is uncertain, random variable, and strictly or rigorously can be mathematically modeled only as a stochastic process, that is a probabilistic variable, as a function of time. In other words, at any given height z above the mean ground level, the wind speed, denoted as u with the argument z, is a highly probabilistic and uncertain random variable that is a function of time and strictly or rigorously has to be modeled mathematically as a stochastic time-dependent process denoted as u, representing the wind speed with the arguments z and t, signifying the height z above the mean ground level and the time t. Now, the function or the probabilistic function that represents the stochastic process governing the wind speed at any given height z as a function of time is a random variable that is highly probabilistic in common man's language. The wind speed at any given height. Z is function of time that is highly uncertain or random. For simplicity, however, in the mathematical modeling of the wind speed at any height z above the mean ground level and any instant of time t, for the purposes of calculating the wind pressures and therefore the wind forces acting on building structures, the probabilistic or stochastic variable u with the arguments z and t, where z signifies the height above the mean ground level at which the wind speed is being considered, and t signifies that the wind speed measured at the height z above the mean ground level is a time variant function, is assumed to consist of two components, that is the stochastic wind speed at any given height above the mean ground level z as a function of time, that is at any instant of time t, denoted as u with the function u with the arguments z and t, may be mathematically modeled as the sum of two components, a mean or steady component, that is denoted as u over bar z at the height z above the mean ground level selected for modeling the stochastic wind speed, plus the fluctuating component u with the wave notation above the alphabet or symbol u that signifies the fluctuations in the wind speed, which are termed as gust at the selected height z above the mean ground level. And since the fluctuating component of the wind speed termed as gust is time dependent, the fluctuating component denoted as symbol u with a wave or tilde over the symbol u is represented as a function of both the height z above the mean ground level as well as the instant of time t. Therefore, to conclude the discussion on the mathematical modeling of the design wind speed or the speed of air, or that is essentially a fluid in motion in the atmospheric boundary layer, the wind speed at any general height z based on the principles of boundary layer flow can be represented using the polynomial equation presented here, that is the traditional boundary layer equation for mathematical modeling of the speed of a fluid in a boundary layer. Since wind is air or essentially a fluid in motion in the atmospheric boundary layer, the traditional boundary layer equation can be used to predict the wind speed at any general height z above the mean ground level given the wind speed or the speed of the fluid or air in motion at a reference height z0 above the mean ground level, which is generally available from the measurements from instruments that are known as anemometers, typically installed at a reference height z0 equal to 10 meters above the mean ground level. Further, the wind speed at any given height z in itself is a highly probabilistic and random variable that is uncertain variable, and therefore requires to be modeled as a stochastic process in mathematical terms, strictly or rigorously. However, for simplicity in the mathematical modeling of the wind speed, for purposes of calculating the wind pressures and therefore the resultant wind forces on buildings, the wind speed at any height z, a time variant function denoted as u with the arguments z and t, can be assumed to consist of two components: a mean component denoted as u over bar at the selected height z above the mean ground level, that is steady and therefore termed as the static component, plus a fluctuating component denoted by u over tilde, that is the symbol u with tilde or wave over the symbol u, with the arguments z and t that signify that the fluctuating component of the wind at any selected height z above the mean ground level is time varying or a time variant function, and due to the fluctuations resulting from the atmospheric turbulence that are termed as gust in the language of, in common man's language, the fluctuating component of the wind or the fluctuations in the wind speed are termed in the common jargon as